So in this video, we will discuss about the value of the current flowing through a series combination of resistor and a capacitor. Suppose we have a series circuit of a resistance and a capacitor like this. That is, we have a resistor of resistance R and a capacitor of capacitance C connected in series with an AC source. This is the AC. And we know the value of the AC equal to V, voltage at any instant, equal to V0 sine omega t, where omega is the angular frequency of the AC and t is the time. Clearly, there is a current flowing through this circuit. Let's say I. We know since it is an AC current, its direction always changes. During the first half cycle, if it is in the clockwise direction, and in the other half cycle, in the very next half cycle, it will be in the counterclockwise direction. Clearly, the voltage V is the source voltage and it will get divided between R and C. This division is in accordance with the vector law, not with the algebra. It's according to the vector algebra. We will discuss that. For that, we have to draw a phasor diagram. That is, let me draw a phasor diagram. This is our x-axis and this is the y-axis. Let this be the voltage, or we can say VR is the voltage drop across the resistor and VC be the voltage drop across the capacitance. We know that the current and the voltage across the resistance are in same phase. That is, VR and current are in the same phase because there is no lag between the voltage and current in a purely resistive circuit. But in case of the capacitor, if we have current in this direction, voltage across the capacitor always lag behind the current, or the phase difference between current and voltage in a capacitive circuit is pi by 2. That is, this angle will be pi by 2. Also, the current leads the voltage. We already discussed that in the video before. If you have any doubt, you can always go back and check the video. Having said that, that is, the angle between the current and voltage is pi by 2. Now let me complete the phasor diagram. Let me draw the voltage drop across the resistor first. Let it be this one. Let's call this as the origin. And let this be the voltage drop across the resistance, where we represent it as VR. We know the current is along the voltage drop across the resistance, so current is along this vector. Since the value of current is small, we need we just drawn a smaller vector. Now, since the voltage across the capacitor lags behind the current, we must draw the voltage drop across the capacitor here. Let it be, let's say, VC. Now we need to find the resultant of VR and VC, and that will be the net voltage drop across the RC circuit, or the series combination of resistive and capacitive circuit. For that, we have to complete the parallelogram like this. And the diagonal of the parallelogram, that is this one, gives the value of the voltage drop through the circuit. Let's call that as V. Let's call this point A. Let's call this point B. And we know this angle is 90. Also this angle is also 90. Current and VC are in a phase difference of pi by 2. Now if you take this triangle, that is OAP, this one is 90. We have this length VR, not I, VR, and this length AB. See, this length and this length are the same, so this will be VC. Clear? And the side opposite to this 90 will be the hypotenuse. Clearly, you know, applying Pythagoras theorem in this triangle OAB, we have OB square is equal to OA square plus AB square. OB is this is V. So V square, the resultant voltage will be, OA is actually VR square plus VC square. Now we know, since I is the current flowing through the circuit, we have voltage drop across the resistance will be IR, and voltage drop across the capacitance will be I times XC. XC is the resistance offered by the capacitor to the flow of AC, or we call that as XC equal to the capacitive reactance. Since the circuit is series, same current flows through this R and C. Now we can substitute these values in here, that is V square is equal to IR whole square plus IXC whole square. Again, XC represents the capacitive reactance. Simplifying, you will get V square equal to I square R square plus I square XC square. That is V square equal to, taking this I square common, we have R square plus XC square. Now taking the square to the right, we have V is equal to root of I square times R square plus XC square. Therefore V is equal to root of I square is I, root of R square plus XC square. Clear? Now if you take the I to the left, we have let me erase this. We have V upon I, that is voltage by current, is equal to root of RC square plus XC square. Also we have XC is actually, the inductive reactance is equal to 1 divided by omega C. That is, omega is the angular frequency and C is the capacitance. Again, voltage by current, you know, voltage by current, when you compare it with the Ohm's law, the ratio of voltage to the current is always the resistance. But here, it's not just the resistance, because we have a capacitance also. So it is the resistance offered by the combination of this resistance and capacitor, and we call that as Z. So Z is equal to root of R square. You can plug in the value of Xc equal to 1 by omega C in here. So it will be Xc square equal to 1 by omega square C square. Clear? Also, we call this Z as impedance. Impedance is nothing but the resistance offered by the combination of resistance and capacitor. Clear? Now we need to find the value of current. See, also we need the value of peak value of current, that is I0 equal to the peak voltage by the impedance or the resistance set. Implies I0 is equal to V0 divided by root of Z is actually R square plus 1 by omega square C square. This is the peak value of current. Now, how will we represent the value of current? For that, this voltage is making an angle of omega t with the x-axis. Let's call this angle as phi. So, we know that the angle XOA, that is angle XOA, is actually omega t plus phi. So, we have the current. See, this is the current. This is the direction of current. The current is making an angle of omega t plus phi with the x-axis. So, we can write I equal to the peak value of current I0 times sine of omega t plus phi. So, this is the value of instantaneous current in an RC circuit. Now, we need to find the value of phi. See, when you look at the triangle, this angle is phi. Clear? That is angle AOB is phi. Now, if you take the value of tan, that is tangent of this angle, we have tan phi. Tan phi is equal to opposite side, that is AB divided by adjacent side OA. AB is actually, this AB is VC. See, AB equal to VC. So, VC divided by VR. Again, we have VC equal to I times XC divided by I times R. You can cancel this I. So, tan phi is equal to XC by R. XC is again 1 by omega C, and on the denominator it is R. So, tan phi equal to, this omega C will move to the denominator. It will be 1 by omega C R. Or in other words, you have phi is equal to, taking this tan to the right, tan inverse of 1 by omega C R. 1 by omega C R. Clear? So, this is the value of the phase angle. Now, you can plug in the value in here in the expression of current. That is we have I is equal to I0 sine omega t plus phi is actually tan inverse 1 by omega C R. Clear? So, this is the final expression for the value of current in an RC circuit, a series combination of resistance and capacitive circuit.